Hello everyone, welcome to 10-Minute Physiology. In today's video, I'm going to give you a short explanation as to how passive transport occurs in the cell. So with that, let's give it a go. So there are three main mechanisms of passive transport. The first are through pores, the second are through gated channels, and the third are through carriers. So we're going to talk about each of these in great detail. Let's start off with pores. So let's just say we have a cell. And remember that we have two compartments of fluid. The first is the intracellular fluid, which is the fluid inside the cell. And the second is the extracellular fluid, or the fluid outside the cell. Now let's just say we have a certain molecule X, and the concentration of X outside the cell is greater than the concentration of X inside the cell. Now inside the plasma membrane, we have a protein, or a transmembrane protein called a pore. So pores are basically transmembrane proteins that act as tunnels or pathways for certain molecules to pass through. So pores are always open, they have no gates, and they're made out of transmembrane proteins. So if we have a molecule of X, X is going to flow down its concentration gradient from the outside of the cell to the inside of the cell. So the next mechanism of passive transport is going to be through gated channels. Now there are two types of gated channels. The first are voltage gated and the second are ligand gated. So voltage gated sodium channels are a great example of voltage gated channels. So in the cell, we have a lower sodium concentration than outside the cell. Now, in order to open these channels, you need a specific voltage. And this voltage change that's going to occur for the voltage-gated sodium channel, for it to open, is going to be something called a depolarization, or an increase in positive charge. So positive charge is going to move to the voltage-gated sodium channel, open it, and allow sodium to flow down its electrochemical gradient into the cell. The next mechanism is going to be the ligand-gated ion channel. So ligand-gated ion channels are channels that are gated by the binding of a ligand. So if a ligand binds to it, this causes the gate to open, allowing certain molecules to pass through it. So for this ligand-gated ion channel, let's just say we have a ligand that binds to it, and then this opens the channel, allowing X to move down its concentration gradient into the cell. Now pores and gated channels are going to follow Fick's law. So Fick's law of diffusion states that the flux, or the amount of molecules passing through a unit area per unit time, is going to be equal to the permeability coefficient. Now the permeability coefficient is going to take into account three things. The first thing is it's going to take into account the membrane thickness. So the thinner the membrane, the greater the permeability coefficient. The next thing it's going to take into account is the diffusion coefficient. So the diffusion coefficient basically describes how easily a molecule can pass through the membrane. So in other words, the easier a molecule can pass through the membrane, the higher this coefficient and the greater the permeability coefficient. And then the last one is going to be the partition coefficient, which basically describes how well a molecule can dissolve in a lipid membrane. And the higher this coefficient is, the higher the permeability coefficient is. So in short, the greater the permeability coefficient, the greater the flux. And then the last part involves the concentration of X outside the cell and the concentration of X inside the cell, and the difference between these two things. The difference between these two things is the concentration gradient. So what you'll notice here is that we need a difference in concentration between the intra and extracellular fluid in order for us to have a flux. Because if they were the same, this would mean that this difference would be zero, therefore the flux would be zero. So we need a concentration gradient in order for a molecule to move. So how would this look on a graph? So if we were to graph the flux of X against the concentration of X for both a pore and a gated channel, what we would see is something like this. So what we notice is that there is a linear relationship between the flux of X and the concentration of X. So in other words, as the concentration gradient increases, the flux increases linearly based upon Fick's law. So the slope of this graph is going to be the permeability coefficient, and the amount of flux is going to be determined by the concentration gradient. So the greater the concentration gradient, the greater the flux. And the greater the permeability coefficient, the greater the slope. So the diffusion through pores and gated channels is going to follow this linear relationship described by Fick's law. So now let's talk about the last mode of passive transport, carriers. So in order to understand carriers, let's look at a random carrier inside the cell. So let's just say we have this carrier protein, which is also a transmembrane protein. And what happens is we have a molecule of X come in and bind to its binding site. So after X binds to the binding site, what happens is the extracellular fluid pore, or the opening at the extracellular fluid, is going to close. So notice that we have two ends of this carrier. The first is the extracellular fluid side right here, and the second is the intracellular fluid side. So right now, both of these ends are closed. So after this occurs, another conformational change occurs, which opens the intracellular side, allowing X to move into the cell. So when X leaves its binding site, this initiates another change, which closes the intracellular side. Now both sides are occluded once again. Then what happens is the carrier will change back to its original area, allowing X to bind again. So how will a carrier-mediated passive transport look on the graph plotting the flux versus the concentration of X? So if we were to take the same graph we took for the pore and the gated channels, what we would see is something like this. So the first difference you should notice is that the curve is hyperbolic. So it approaches a maximum value of flux. And this maximum value of flux is called the maximum flux, or Jmax. So what this is saying is basically for carriers do not have an unlimited flux. They have a maximum flux which the carrier can build up to in this graph as we see here. So the carrier has a maximum flux because the carrier is able to become saturated. So in other words, if you have enough solute, the carrier will be saturated with solute, which means that the carrier is working at its maximum capacity. So this is the maximum that this carrier can work. So it has a maximum flux that it can generate. Now the next point is going to be the Km. So Km is the solute concentration at which Jx is half of Jmax. And the lower the Km, the higher the affinity. So this graph is going to follow this relationship right here. So this is called the Michaelis-Menten equation, and this is the same equation that we see for enzymes. So this equation is going to govern how carriers work. So in summary, we talked about the three main modes of passive transport: pores, gated channels, and carriers. We also talked about how simple diffusion follows Fick's law and how carriers follow Michaelis-Menten kinetics. So I thank you for watching this video, and I hope to see you in the next one. Thanks for watching, and I hope to see you next time.